Work, energy, power. You hear these words all the time, right? But what if I told you their real meanings, their physics meanings, are the hidden rules that govern literally everything that moves in our universe? Let's dive in and unpack this.
So think about this for a second. What could a massive roller coaster, paused at the very peak of its highest drop, possibly have in common with a simple stretched rubber band just waiting to snap? On the surface, it seems like absolutely nothing, right? Well, it turns out they share this incredible secret, and by the end of this, you are going to know exactly what it is.
All right, first up, work. And I'll give you a little heads up, the physics definition of this word might just challenge your everyday idea of it. We're not talking about your 9-to-5 job or, doing the dishes. This is something else entirely. See, in the world of physics, work has a couple of really strict rules. First, you've got to apply a force. Second, that object has to move. It has to be displaced because of that force. It's all wrapped up in this neat little formula. F is your force, d is the distance it moves, and that cosine theta part, that's the secret sauce. It tells us how much of your push or pull is actually going in the same direction as the movement. That angle we just mentioned, it's pretty much the whole story. If you're pushing a kid on a swing, your force is helping the motion, so you're doing positive work. Now friction, working against a car's tires, that's negative work. But here's the one that messes with everyone's head. Imagine you're carrying a heavy bag of groceries. You're holding it up, applying an upward force against gravity, but you're walking forward, horizontally. Because that force and your motion are at a 90-degree angle to each other, you are doing zero, and I mean zero, physics work on the bags. Now your muscles might be screaming at you, but in the language of physics, no work is being done there. So let's put this to the test. You go up to a solid brick wall. You push with everything you've got. You're sweating, you're straining, you feel like you're working incredibly hard. But have you done any physics work on the wall? The answer is a clear and simple no, not a bit. Why? Because the wall's displacement is zero. Remember the rule? No movement, no work. It's as simple as that.
Okay, so if work is the action, what's fueling it? What makes it possible? Well, that brings us to energy. And the best way to think about it is this. If doing work is like making a purchase, energy is the money you have to have in your bank account to make it happen.
So the official definition of energy is just that, the capacity to do work. It's the juice, the stuff that gets things done. And notice its unit is the joule, the exact same unit as work. That is not a coincidence. It's a massive clue that these two concepts are basically two sides of the same coin. And the thing is, energy is absolutely everywhere, and it's constantly changing costumes. It's the chemical kick in a battery, the electrical current in the wall, the warmth from the sun, the sound coming from your headphones. It is the universal fuel for, well, everything. Now, for our purposes today, for the story of how things actually move, we don't need to get lost in all those different forms. We can zoom in and focus on just two key types of what we call mechanical energy. First up is kinetic energy. Honestly, this is the easy one to get. It's the energy of pure movement. Anything that's moving has kinetic energy. And you can see from the formula, the more mass it has, or the faster it's going, the more kinetic energy it's packing. A speeding freight train has a ton of it. A crawling snail, yeah, not so much. And its counterpart is potential energy. This is the stored up stuff, the energy that's just waiting to be unleashed. And hey, this is the answer to that question from the beginning. The roller coaster at the top of the hill is loaded with potential energy because of its height. The stretched rubber band is full of potential energy because of its deformed shape. It's the energy of what could be. Okay, so we've got work, and we've got energy. Now for the really cool part, the aha moment. This is the beautiful, simple principle that ties it all together. So the big question is, how does this connection actually happen? We said energy is the capacity to do work, but how does that play out? When you push a stalled car to get it moving, how does your work magically become the car's energy? And here it is. The answer is so simple and so powerful, the work-energy theorem. It just says that the total amount of work you do on an object is exactly equal to the change in its kinetic energy. You push a car from a standstill, and the work you put in becomes its energy of motion. The brakes on that car do negative work to drain that energy away and bring it to a stop. It is a perfect, balanced, one-to-one transaction. This brings us to a law of the universe that is as fundamental as it gets. You can't create energy and you can't destroy it. It just gets moved around and changes form. But to understand how this cosmic accounting really works, we need to meet the two types of forces that act as the bankers. On one side, you have the neat and tidy ones, conservative forces like gravity. They're predictable. If you lift a book, the work you do is perfectly stored as potential energy. and you can get all of it back when the book falls. Then, you have the messy ones, non-conservative forces, like friction and air resistance. They're like a transaction fee. When you push a box across the floor, some of the work you do is just lost as heat. It warms up the floor a tiny bit, and you can't get that energy back. It's gone from the system.
So what does this all mean? Well, in a perfect world, a system with no friction or air resistance, the law of conservation of mechanical energy is king. The total amount of energy, the kinetic plus the potential, never changes. It just swaps back and forth. The roller coaster trades its potential energy at the top for kinetic energy on the way down, but the total in the bank account always stays exactly the same.
And what's really cool is that potential energy even tells us how stable things are. A ball sitting at the bottom of a bowl is in stable equilibrium. It's at its lowest possible potential energy, and if you nudge it, it'll just roll back. But a ball balanced perfectly on top of a hill, that's unstable. It's at maximum potential energy, and the tiniest little push will send it tumbling down. It's kind of like us on a Monday morning, right? Nature always seeks the path of least resistance, that lowest energy state.
All right, we have reached the final piece of our physics puzzle, power. So far, work and energy have told us if something can happen. Power tells us how fast it can happen.
Power is simply the rate of doing work, or how fast you're spending your energy. You and I could both lift the exact same box up a flight of stairs. We'd do the same amount of work. But if you run up the stairs and I walk, you are generating way more power because you did the same work in much less time. That measurement, joules per second, has a special name, a watt.
And this formula shows us something really cool about power when things are in motion. Power is a combination of the force you're applying and how fast you're going. This is exactly why a sports car needs a massive engine. It's not just about hitting a crazy top speed. It's about having the raw power to get there quickly while fighting against forces like air resistance.
And just to give you some perspective, the old term horsepower was literally invented to compare the new steam engines to the power of a draft horse. As it turns out, one of those horses is equivalent to about 746 watts. It's a fun little bridge between an old, familiar unit and the modern scientific one.
So let's bring it all home. Work is the action of transferring energy. Energy is the capacity to perform that action. And power is how fast you do it. We live in a world that is obsessed with power. Faster cars, faster computers, faster everything. But if power is just the rate at which we spend our energy, what does our constant demand for more and more of it say about our relationship with the energy resources that fuel our entire world? It's something to think about.